Have you ever watched a wave and noticed how at a certain point it breaks, curling over itself? There's something fascinating about the motion. To understand why waves at the beach behave this way, we need to step back and explore what a wave really is. And to do that, we need to explore energy. You see, waves are not just what you see at the beach. Waves cause a disturbance in whatever medium they're traveling through. They are the vehicle for light and sound, the answers to questions about how earthquakes work, and more. I'm Science Mom.
And I'm Math Dad.
Grab a slinky, a blanket, and some ping pong balls because today we're going to make waves. Have you ever looked at waves at the ocean and wondered why they curl over at a certain point? And why on some beaches you get big waves that curl a lot and other beaches you don't?
Yeah.
The answer has to do with how deep or shallow the beach is, and of course, how the wave is moving. But let's back up and talk about what a wave is. Quick shout out to Maxwell from Ontario. Hello to Remington Wolf and Happy Hedgie. Happy birthday tomorrow. To Violet James, Leaf, Max, and Molly watching in Utah. It is good to have you guys with us, and special welcome to you if you're watching the replay.
I'm excited because waves, you can get into math when you're doing that. We're not going to get too much into math today, but we are going to talk a little bit about modeling. So I'm excited. I did a lot of the notes for this section.
Math Dad did. He is excited for today's lesson. So what page in the notes are we going to be on today, Math Dad?
Oh, now you're asking me questions I don't know the answer to.
You'll find out in just a minute. We have slinkies, some small slinkies, because slinkies are a great way to model the difference between two of the main types of waves. Now, waves are a form of energy. They're energy moving through something. And a wave can be longitudinal. That means that the energy is moving the same way as the wave. That's kind of like doing this with the slinky. See, my hands are moving the same way.
Expanding and contracting type.
Or they can be transverse. And now my hands are moving the opposite direction that the energy moves.
So that's when we're seeing a wave go up and down.
Up and down, yes. And we'll talk about that again in just a few more minutes. There are some bigger words we'll be using in this lesson.
Let's say those two words one more time, though. So it was longitudinal when it was
longitudinal,
just traveling back and forth. And it was transverse when it was going up and down.
In fact, if we do an overhead view real fast, it's a little easier to see if we're overhead. So longitudinal is when you are, I could kind of bunch up some of this and make it more and then let go. Or I can go like this, going back and forth.
Yeah, okay. So that's
and then transverse. Transverse with a slinky this length is actually a little bit hard to see. So we have a video where we have a bigger one that we used, and you can see it just a little bit better.
All right.
So first, if you don't have a slinky, you can still make waves. I took a sheet, and if I input some energy, you can see how the wave travels all the way down the sheet, and those ping pong balls kind of bounce off to the side. And if I keep a repeated motion going, I can even get waves that look kind of like what you see at the beach.
So it's pretty cool. The wave just keeps traveling through it. It doesn't die immediately.
It doesn't.
There's some air trapped under it.
It keeps traveling all the way through.
So that energy gets transferred over that long distance.
Yes. And then here's an example with a longer slinky. And you can see here we're making a transverse wave because Math Dad moves his hand to the side, and that's perpendicular to the direction the wave is traveling. We'll do it one more time in slow motion. It's very satisfying, isn't it?
It is. Well, it bounces back and forth from one end to the other. So the energy is transferring with a lot of efficiency.
It really is. Now, transverse waves are the waves that we have in light and at the beach when you see water moving up and down like that.
It's a lot more visible.
Mm-hmm. Longitudinal waves.
Ooh,
that's what we're seeing right now.
So I'm coiling it up right now.
Pulling it up.
And I'm going to release it. And you've got to look closely because it doesn't show up super clearly. But I let go and
then you can see it. That the compressed part goes down and up. This is what makes sound waves. So when someone hits a tuning fork, the tuning fork is vibrating, and those vibrations cause air molecules to move, and then it's a compressional wave that travels through air. And if you go to outer space, then there's nothing for the wave to travel through, and so the sound wouldn't go anywhere. It has to have something to travel through.
Well, and there's this interesting mix as it's vibrating side to side. So that here we have these strings that are actually vibrating. So if you play a violin or a guitar, they're going to vibrate just like this. There we're seeing the transverse is what we're actually seeing, the back and forth side to side, but it's creating so a compressional wave that's a longitudinal wave, because that's what sound waves are. They're longitudinal waves that the vibrations are traveling through a medium, through some substance. Typically that's air, but sound can travel through water.
It can.
And sound can travel through solids. In fact, it travels through solids faster than it travels through air typically. And it will kind of depend on what the solid is made of.
All right, let's open the notes. If you have the notes, I hope you will follow along with us. We're going to fill some things in and learn about the different parts of a wave. So we are on page 89, and we're going to talk a little bit about the two simple activities that we showed you, how you can take a sheet, and we had our blanket map, but really any sheet or thin cloth will work. And if you lift up and then put down one side, you can see a wave travel from one end to the other. And the part where it lifts up and is high, we call that the crest. And then the part that is low, that's called the trough. And the distance from crest to crest, that's the wavelength.
So if those crests are far apart, then we say it has a large wavelength. And
long wavelength.
Long wavelength. And if they're close together, we have a short wavelength.
Something kind of cool about our slinky, when we took that big slinky and stretched it out, when we do a transverse wave and Math Dad will move his hand to make it vibrate, the time it takes to travel down one end and back is the same whether we do a really big motion or a really small motion. But which one's going to have more energy?
Well, the big motion is going to have more energy.
The big motion is going to have more energy. So look back here at our picture. A wavelength can be long or short. And if it's long, you have something like this. If it is short, then that's going to have a lot more energy. But they're both waves. They're both traveling at the same speed, especially with something like light. The speed of light doesn't change. But if you have a short wavelength, that's a lot more energy.
So when we're making sounds, something interesting is happening. So you're thinking about like a violin string vibrating, the frequency, or the shorter the wavelength, the higher the pitch is going to be. But the taller the waves, the louder it will be.
You can have all of those things change with different waves. Two
different phenomena going on. So this word amplitude, it's actually a measure from the baseline up to either the crest or down to the trough. So that amplitude tells you how tall your waves are. And so a higher amplitude is going to be a higher volume when it comes to sound.
Now, the blanket activity and the slinky activity, I hope you have some fun just playing and experimenting with waves. But we're going to talk a little bit about
modeling.
Math Dad was so excited about this. So I'm going to turn the lesson over to Math Dad real quick, and I'll be watching the chat for questions. Take it away, Math Dad.
Okay, so one more time. Up on this page, looks like I used a different name. I called it the peak instead of the crest. There are lots of different names that we could apply and that you'll see, but the words I want you to know for today are amplitude, so it tells you how tall you are from the baseline, and then wavelength. And look what I did. This time I drew it as the distance between two of the troughs, because we're at the bottom of the wave. Is that going to be the same as the distance between two of these crests, the peaks of the wave?
Totally. Yep. That will be the same.
No. So we might call this a sine wave in math. It's kind of fun, but that's trigonometry. That's a high school topic when you'll get into the mathematics behind these waves. But we are going to look at some uses of waves in modeling. So models are tools that mathematicians use or scientists use to predict outcomes. And almost always there's going to be some math involved when you do that. But you usually don't have to get too deep into the math to understand the beauty and power of these models. So phases of the moon is something we talked about just this last week. What you'll notice, so it looks like I went from a full moon here to a new moon at this end. Well, that's going to happen every single month. It's going to cycle, right? Go all the way from full moon to full moon. Ooh, how many days was it?
Not exactly every single month. If we followed a lunar calendar instead of a real calendar, then we would have the months offset. So June would be in the summertime if you live in the Northern Hemisphere when you were a kid. And by the time you were a grandparent, June would be in the winter. And so that's why we don't follow the lunar months, because they're offset just a little bit. We don't have exactly 12 lunar months in a year. We have
a little bit more.
A little bit more.
So in this sample problem here for phases of the moon, I wanted to label, what was the amplitude? What would its meaning be? What about the wavelength? And what about the crest and the trough? So let's see what I came up with. So I said for the amplitude here, so the distance from the baseline up, well, 100% visibility is what we would get at the top.
So that's a full moon?
So this would be full moon at the top and new moon at the bottom where there's 0% visibility. But so 50% visibility would be how I would label the amplitude.
Ooh.
Now, what about the wavelength for our model here? Well, how long is it between new moon to new moon?
29-ish days.
Yeah, it's 29.5, I think, is more accurate. But I mean, here, we haven't given you enough information to do terribly accurate models. So we're just coming up with guesses, something that would be reasonable. So I wrote 29 days. And so I was able to fill in the meaning of all four of those terms. We had the amplitude here, the wavelength here, the crest or peak, and then over here, we even had the trough, the bottom of the wave, and what they would actually mean for us. All right, so let's move on. And pretty much anytime you have something that's cycling like this, it's repetitive, it's going to repeat often, you're going to get this type of thing. So a wave function.
You can use a wave to model pretty much anything that has a cycle.
Yeah. All right, so hours of daylight in a day. So we live in Las Vegas, Nevada. During the peak of the year, the longest days, I think it's around 14 and a half hours of daylight. Now, this depends on where you live as to when you will have the longest days of the year. So you might fill this out very differently than I would. If you live up in Alaska, you're going to get a lot more daylight in the summer and a lot less. And that would mean that your waves are going to be taller than my waves. But all right, so for me, I'm going to write that out, that maybe 14.5 or 14 and a half hours would be the maximum amount of daylight that I have. But what about the minimum amount, Science Mom? Any guesses?
Oh, minimum amount you're talking about, like in the winter time?
In winter times, you get close to Christmas, you hit the winter solstice.
I guess 8.
Yeah, I think it's a little more than that here. I think it's closer to 9.5. But yeah, sure feels like a much shorter day. That's a 5 hours difference between summer and winter here. And for some of you, it'll be less than that. For some, it will be a lot more. Okay, so assuming those numbers are realistic, the amplitude is always going to be half of that difference.
Ooh.
So it looks like the total difference from 14 and a half to 9.5 is about 5 hours. So half of that would be 2.5 hours. 2.5 hours would be our amplitude. Okay, but what about this? I go from...
So how long does it take to go from winter solstice, when we only have 9.5 hour days, to winter solstice again when we only have 9.5 hour days?
Or from summer solstice to summer solstice. The same question, right? And the answer is
one year.
One whole year. Or I could write that as 365 days. So a very, very different scale here on this wave. I might call this one a really slow wave. It takes a whole year for things to happen. Okay, what about modeling high tide? So that's something we've talked about, where the tide is going to come in and it's going to go back out and it just kind of repeats itself. It doesn't repeat itself exactly each time, but it's approximately a wave function. So in this case, I'm just going to make up some numbers because we talked about tides and how it really depends on where you're at. But I would say typically a high tide is going to come in and raise the water level 5 feet. So does that sound realistic, Science Mom?
Sure.
Okay, so 5 feet. All right. And in that case, I would probably say the peak level comes at positive 5 feet, and then the bottom negative 5 feet relative to sea level. I'd probably use the positive number and negative number because I would think of this dashed line as sea level. And all right, so how often does that happen? So how many high tides do we have each day? Well, we
Usually
said
2.
Yeah, we typically have
Usually
2 high
2.
tides per day. So the distance from one high tide to the next high tide, or one low tide to the next low tide, I'm going to say is about 12 hours. Not exact, but it's close to that. So these are some examples of mathematical models that involve waves. And you can actually even come up with equations for those so that you can make predictions in the future. You can say, ooh, when will high tide happen in July? And you can map that out and actually figure it out. And since we've mapped out the cycles of the moon, we know where the moon will be at each time. We're actually able to predict the tides. So all those predictions end up being closely related to each other.
That is pretty cool. Math Dad, if you can pull up the slide I made, I want to talk just a little bit more about ocean waves. And I saw some good questions in the chat about ocean waves as well. So why do we get ocean waves? Well, just like when we were looking at our slinky and you saw the transverse wave that Math Dad made going across the floor, when you think of an ocean wave, you have this transverse wave where there's energy going up and down as the wave is moving forward. But once this wave has something on the bottom, because the wave is really like there's a wave kind of going this way too. There's motion underneath. Once it hits and the height of the wave hits something that is about 1 to 1.3 times that distance below it, then it starts to slow down up here. But this part is still going forward, and that forward momentum pushes over and causes it to break.
So you got this wave, it's slowly moving in this direction, and you're saying the top is moving now, but the water on bottom stops moving.
It's slowing down.
It's slowing down, so the water on top is going faster, and that's what's causing it to crash down. The waves break.
Yeah, and if you have a shallow beach where it's going up at a little incline, then you don't get a wave that actually curls over. You just kind of get the nice, it goes a little white and settles in gently. But if you have really deep water, and then all of a sudden you get a reef, that's when you get these waves that curl.
Oh, yeah. And I've
cool?
seen both types of beaches where sometimes the waves are just boom, hitting really hard or breaking hard, and others where it's pretty gentle.
And if the wave is higher, if the wave was this high instead, then that means that way back here is where it's going to start breaking instead of up here, because it'll be hitting that ground sooner. So the bigger the wind is and the bigger the waves are at beach, the further out you'll get that curling over.
And is the wind what's creating the waves?
Surface waves are often formed by wind, yes. And what about a tsunami? So anytime that you have movement in the earth, like an earthquake, you're going to actually create both types of waves. Because if there's a big movement, there's going to be compression that's going to push and make a compressional wave that will travel through. But if there is shearing, like you have a fault line where all of a sudden things shift, then that can create transverse waves as well. And with a tsunami, if you have an earthquake underwater and a big piece of land moves, then all the water on top of it moves, and that creates a transverse wave that will travel until its energy runs out. The longer it travels, the less energy it has, and so it will eventually die out. So there were some good questions about that.
Yeah. Okay, so you bring up earthquakes. You mentioned something interesting. This was an answer to one of our questions, big questions for this course, was how in the world could a scientist know that the Earth had a molten core? Because we can't travel down there. It's just way too far. We can't even get down to the mantle. But somehow we know what the center of the Earth is made of. I mean, that sounds kind of ridiculous at first glance, but somehow we do know that. And if I remember right, Science Mom, it had to do with the way that waves traveled through the Earth.
Yes.
You said that there were multiple types of earthquake waves.
And some of them can pass through liquid and some can't.
So you've got the compression waves that probably would travel through the earth better typically. And then you've got the transverse waves, which are going to be more visible to us. And yeah, so that's interesting. There really are those two different types of waves. Light makes waves. So
light travels as a wave.
Yep, we've got this electromagnetic spectrum. And yeah, so it's all governed by waves, although those are very fast waves. We saw that the one wave took a year to the daylight cycle wave, but
the speed of light is very fast.
Yes, light does not hang around. It's going.
All right, we have a very different where in the world mystery today, and it's a question that I have been thinking a lot about. Where in the world should we move? We want to relocate somewhere greener and with mountains and more trees, because Science Mom really misses trees. And so Boulder City, Nevada, where we live right now, I have to say it's out of the frying pan and into the fire in terms of the housing market. We were looking at Logan, Utah, Corvallis, Oregon, Olympia, Washington, really anywhere in Utah, Oregon, and Washington. And the housing market is so competitive right now. It's kind of ridiculous. So if you have a thought or suggestion for us, feel free to email us. I would love to live in Alaska for a little while. That's what I told Math Dad. If we're looking anywhere, we should move in Alaska. I know we have some students in Alaska.
I don't know if we could handle Alaska. We're seeing California, Ottawa, Madison. Yeah, see, several options there.
So in answer to questions that I saw in the chat, we do not know where we are moving yet, but we are hoping to get it figured out soon. And
I want...
Oh, I thought we were ready for...
No. I've got one more wave application.
One more wave application. And then Math Dad is going to quiz you guys with itempool.com/sciencemom/live.
Okay. So this is something called a predator-prey model. And so suppose you had this ecosystem that really only had two animals. You've got lions and you've got gazelles. And I think we know how this would work. So I'll start at the bottom. If there were very few lions, well, that would mean that there could be a lot of gazelles. The gazelles would start reproducing and the gazelle numbers would go up. So you'd end up with a large population of gazelles. But what would result from that, Science Mom, if you had lots of gazelles?
Lots of gazelles. Well, then there's going to be more food for the lions to eat.
That's
then there's going to be more lions.
Yep. So the lions start growing. Ooh, then you get lots of lions. Well, what's going to happen to the gazelle population once you have lots of lions?
Then they're going to eat a lot of the gazelles, and there aren't going to be as many gazelles.
Oh, the gazelle population is going to drop. Okay. But once the gazelle population drops...
Then those poor lions are going to be really hungry because they don't have enough gazelles.
That's right. Oh, okay, so the lion population is going to drop. Well, if there aren't many lions, the gazelle population is going to start growing again. We end up with a cycle like this. And you can model this with a wave. So what you're seeing right here, I have two things that are going up and down. One of them is going to be the lion population, and one of them is the gazelle population over time. So sometimes there were lots of lions and few gazelles. Sometimes there were lots of gazelles and fewer lions relative to each other. But yeah, so here we're graphing versus time. And well, we're seeing this change in our predator-prey model. Or we could do things differently here. We could plot the number of lions on one axis and the number of gazelles on the other axis, and this picture would tell the same story. Ooh. So I didn't write this in, but so this was gazelles for the dashed line, and it was the lions for the solid line. But yeah, here as the number of gazelles is growing, but then the number of lions starts growing as we get bigger in the horizontal direction. So the number of gazelles starts shrinking, got lots of lions and not as many gazelles. But then the lions start dying off.
Isaac says he hopes that Hobbes stays alive during that cycle.
Yep.
Of all the tigers, Hobbes is my favorite from Calvin and Hobbes.
So yeah, they call this a predator-prey model, and individually you just end up with these wave functions. And my challenge for you in the notes was to make up your own predator-prey model.
Ooh.
Choose a predator and a prey, see if you can plot what would happen over time. And notice I didn't throw any numbers in here. It's just kind of a hypothetical, and maybe the scale means something. Maybe it doesn't mean so much. But yeah, see if you can come up with your own predator-prey model.
Could it even be an herbivore, like rabbits and clover? Because if the rabbits eat all the clover, then there aren't going to be as many rabbits, right?
Okay, that's interesting. I hadn't thought about that, but I don't see why rabbits and clover wouldn't work. The rabbits are the meat eaters of the animal, of the plant kingdom, as far as they're concerned, right?
Yeah, these wave-type cycles occur throughout so many different areas. So we hope you enjoyed just that little dip into some charts and looking at wavelength. And now it is time to go to itempool.com/sciencemom/live, because we have prepared some questions for you guys. And I want to wish a very happy birthday to Maxwell, who turns 10 tomorrow. Happy birthday, Maxwell. We hope you have a great birthday.
Can't get my video to exit.
Oh no, Math Dad.
But I'm going to jump into some questions here. Well,
cross your fingers, for Math Dad, that he can get...
It's a full screen video. Curse you, full screen.
He did it. He did it. And then I saw several questions about like what we want with climate and where we're relocating. I would really like a forest. I would love to be closer to the ocean. And I would like about 40 inches of rain a year. I really miss rain after having lived in the desert for how many years now? 11, 12 years?
I think it's only 9 or 10, but
9 or 10.
It must seem like longer. Poor science mom.
All right. Now are we ready?
All right.
Here we go.
So we've gone to itempool.com/sciencemom/live. And
our first question is about wavelength. The shorter the wavelength,
the higher the energy, or the lower the energy?
Which one? So if you have a wavelength and then you change the energy of that wave so the wavelength is shorter, will the energy be higher or lower?
So this is an interesting question. This is one we talked about a little bit with light.
We did talk about it just a bit.
We talked about that electromagnetic spectrum. So does shorter wavelength have lower energy or higher energy? This one's pretty close, Science Mom. 34 to 31.
Ooh, it's almost died. Maybe you will stump them, Math Dad. We did, and it's funny, I'd seen in the chat several people saying, harder questions, harder questions. Well, today's the harder question day because we went through some stuff pretty fast.
Harder questions by teaching faster. I like it. All right.
The higher the energy is correct.
Oh, so they got it wrong.
This one was really close. Math Dad gets a point for stumping, but he shouldn't let it go to his head because the unbeatable science kids are going to be coming back.
They're going down, Science Mom. All right, so when we say then that the higher, you get higher energy for shorter wavelength. If it's shorter wavelength, that means it's got to be traveling up and down more often, and that does coincide with higher energy.
Yes, let's pull this up real quick and let me just draw this. So if you have we're talking about light, a light with a lot of energy is going to be really short wavelengths. So UV light, very short wavelengths. And then blue, red light would be longer wavelengths. And I used the wrong colors for that, but you get the idea.
Just a sec. I think I can do this. What's this fancy schmancy stuff, Science Mom? Oh man, that didn't work at all.
Yeah, there we go. A green screen is kind of fancy.
Here we go. Now I can draw on the screen.
Oh, wow. Oh. That is pretty fancy.
So yeah, if the waves are going up and down over and over again, that's going to require lots of energy to get such a short wavelength. Whereas if
the wavelength is really
really big
far
wavelength
apart, that's not as much energy.
So we saw this on like the ultraviolet light ended up being much higher energy, and the infrared light ended up being much lower energy on our spectrum. All right.
Next question. Wavelength is a measure of, is it the height of the wave, the average height of the wave, the maximum height, or the distance between the crests of the wave? Which of those is wavelength?
And 11 votes for one. 18 votes. So doing pretty well here.
And then Amaya has a great question. Could really high waves create waves in the ground, like the way that the sheet had waves? And I'm going to say probably not, because most ground is not flexible enough. But they're
just much smaller.
Well, there is this thing called liquefaction zones. So in geology, if you're looking at especially areas that have a lot of clay and a lot of groundwater, there are certain types of soil where if an earthquake passes through them, the soil will actually become liquid and it will move and flow just like a liquid. And this is not super common, but there are a couple times where an earthquake has happened in an area with a liquefaction zone, and then you'll see an entire area that felt like solid soil, but when that energy passes through it, it flows like liquid.
Often, though, you're going to see waves just being much smaller and almost not measurable. Like an earthquake has to be pretty big before you can even feel it. Small earthquakes are too little for us to even feel.
But they're happening all the time. So seismologists are gathering a lot of data about earthquakes all the time. But yeah, it's only the really big ones that can cause the ground to actually shift and break.
All right, and they got it right.
Go,
so
unbeatable
the wavelength
kids.
is the distance between two crests or two troughs of a wave. Very good. All right, question number 3. Sound waves are what type of waves? Are they longitudinal waves or transverse waves? And I'm not going to tell you or any hint specific to sound waves. I'll just remind you, though, what are those two things? So a longitudinal wave was a wave that was traveling in the same direction as the force, where the transverse waves are actually traveling perpendicular. That visible trough and crest, a lot easier to see. There's the longitudinal waves are more compressional waves. And we
did go through this really quickly. So
this is it. I'm going to trick you again. Science, Mom.
Can you count it as tricking if you go too fast through too much new material? I don't think that counts.
Whatever. I'm crushing them.
This is like a calculus question for...
Do you hear that? That's the sound of kids crying everywhere because math dad is getting them. All right. All right. Let us finish and reveal. And the answer is longitudinal. So yeah, sound waves are actually more like a compressional wave. They're not vibrating in this direction. Sometimes we might model them that way, but yeah, really they're the compressional waves.
So the compressional waves, it's like a compressed bit of slinky sliding back and forth along this, right. Whereas a transverse wave is up and down. Right.
Well, but the interesting thing is they're kind of caused by something that is a wave that is actually transverse. So if you hit a drum, for example, the head of the drum will actually be vibrating up and down. So that's going to be a transverse wave. But the sound it's producing is a longitudinal wave as it travels through the air. Or same thing, we saw the violin strings in that video earlier. They were actually vibrating up and down. So you're seeing the transverse wave, but the sound that's produced is a longitudinal wave.
And the real thing to remember here is that waves are energy and vibrations produce waves. There was one more question I want to answer really quick in the chat about tsunamis. And when does a tsunami break? When are you going to get a tsunami that will curl over? It all depends on the type of the tsunami. But usually it will break and curl a lot farther out from the coast because it's a much bigger wave.
That makes sense.
Yep.
Yeah, so tsunamis are kind of scary. So just like you're saying, so every sound we hear is a result of vibrations. Is that accurate? So what about like a squeaky door hinge? Are you telling me there's some vibration happening on a squeaky door hinge?
Yes.
Oh, so there's some friction?
There's some friction. Something is moving and making something vibrate, and then that vibration is what we hear. And when we're speaking right now, it's our vocal cords vibrating that make the sound. And then as the sound waves come out, our mouth and our tongue shape them so that then that's how speech happens.
So we're providing the air that's making the energy that's making the waves. If a door hinge is squeaking, it's because we're providing the energy that's causing that vibration. Yeah. That's really cool. Okay.
So I just want to let you know, Math Dad, the unbeatable science kids are not, they're not crying.
No.
They're like, we're tied, and this question's the tiebreaker. That's what they're saying. So.
2-1, Science Mom. 2-1. All right. Our next question. If a tree falls in the woods and nobody is around to hear it, does it still make a sound?
I just want to know what you marked as correct for this one, because I feel like this one you can argue.
So, no hints, Science Mom. No hints. No hints at all. All right. What in the world? 37-1? I expected this one to be...
You expected this one to be tied?
Pretty close.
I'm really curious because I'm not sure which one's the winning one.
Whoa.
We will find out.
I remember my third grade teacher asking us this, and my class got in a big argument over this question. And
Science Mom Amber says that they're providing us with wave-like data on the answers.
All right, well, let's see what they said. And they voted for yes, it still makes a sound.
That's the answer I like the best. But you will find people who will argue this one both ways. It is not a clear-cut question.
Okay, so what's happening with this question? Why do some people say one thing and others? Because you think we would all know what a sound is, right? We've all been alive. We've been around. We use the word sound at least once a day.
Yes. So if a tree falls, is it going to crash into the ground and that vibration is going to send out sound waves and air molecules are going to be moving? Absolutely, yes. But if there's no ear to pick up those sound waves and interpret them as sound, then some people argue that it doesn't make sound because nobody heard it. Right.
So they're using the word sound in two different ways. Even though it is a word that we all use, maybe we don't actually all use it quite the same. So they think a sound is something that arrives at an eardrum, whereas I would say if the sound wave was actually created, then it made a sound. Kind of like if Science Mom is wearing a green hoodie here, well, if I'm not looking at it, is it still green? Well, of course it's still green. I think of sound waves the same way, but you will find lots of very intelligent people who will argue it the opposite way. I was reading an article just this morning that tried to make it clear, like obviously, as it said that if the tree doesn't make a sound if no one's around to hear it. And oh, really? Is it that obvious?
So now it is 2-2, Math Dad. Next question.
But that one didn't have a right answer.
But the science kid's got it right.
All right, this one's for all the marbles. The last question of the day. We're going to compare a thin violin string to a thick violin string. So a thick violin string will play a note that is lower or higher in pitch because it vibrates faster or slower.
Whoa, Math Dad, this is a hard question.
This is the one.
So I think if you've ever played the violin, maybe this will help because you can just look at a violin and the lowest note, is that going to be the thin string or the thick string? Kind of think of that. And then think about that string. And is it going to be easier for it to move or a little harder for it to move? That's my best job at giving you a hint, you guys. Which will it be? All right. What do you think, Matt? Was that a good hint? I'll allow it. All right. We got one category that's got more than half the votes. Maybe they'll get it. I don't know. The suspense. Saw someone in the chat say, we're done for. But then I'm seeing several other people in the chat say the right answer. So. Oh. All right. Let us finish and reveal. Woohoo! Lower and slower. So if you look at a violin, the highest pitch string is super, super thin compared to the lowest pitch string. That lowest pitch string is really thick. And the reason that it makes a lower sound is because it's thicker and it doesn't vibrate as easily. Yeah, so it's going to vibrate. It vibrates slower. Slowly. Yeah. And yeah, that ends up giving us a deeper pitch. That is exactly right. Good job. Nicely done. And yeah, I think it's just because it's a stronger string, it's going to be harder to get it to vibrate. Good job, science kids. So I'm gonna go with the first victory dance that I see in the chat, whichever one is requested first. Oh, they're talking smack now. Oh, you guys got lucky today. We've been so busy, and I see Amaya request Orange Justice. We're gonna do Math Dad's attempt at the Orange Justice. We've been so busy researching where are we gonna move next. We have not yet filmed new dances, but this one's a classic. Also, don't have a lot of room to film. Okay, let's see. I enjoyed this one. Makes me laugh every time I see it. I hope that you guys have a wonderful day. Work hard, grow smart. We will see you next week learning all about rivers and lakes.
Good luck finding some waves to model your equations and cool phenomena.